Okay, and let me just got it. I should start the recording part as well, and then share screen.
Okay.
Okay, so let's start the. Hope you guys can see the screen.
Yeah, we can. Yeah.
Perfect. So off to you, Pawan.
Okay. So let's get started. Welcome everyone to this RFC's We Love session. Thank you for taking the time out this Friday evening and deciding to attend this session. My name is Pawan Biram. I work for Juniper Networks as a distinguished engineer in the routing protocols development team. I'm a board member of the India Internet Engineering Society, or the IIESOC as we call it, and I'll be the host for this session today. We have three great talks lined up for you today. Before we get started with those, let me spend a few minutes on some introduction notes, if you will. Can we go to the next slide? This is our 26th meetup. Half of those have been virtual. Hopefully, we'll have an in-person session very soon. For those of you who are new to this, these RFCs We Love sessions are organized by the IIESOC. In these sessions, we typically pick topics from IETF drafts or RFCs and discuss those in detail. Uh, IIESOC also organizes various other events. There is Connections, which is an annual event that we have been organizing since 2017. We typically organize this just before one of the IETF events. We also have a partnership with INTC, which is the Industry Network Technology Council. And together we have been organizing seminars on IPv6 and security topics. So please do keep an eye out for announcements or updates on those. Talking about IETF, there is an IETF meeting right around the corner. It's coming up late next month. The meeting is in Yokohama, Japan. As always, remote participation option is available. There is also a fee waiver option available for remote participants if there is a need to avail one. So please do check that out if you're interested. Next slide. Let's do a quick metrics gathering exercise. If you can click on the poll button on your Zoom client and participate in the poll, that would be greatly appreciated. Okay.
So we have some people for them. This is our first meeting. So welcome for being here. I'm going to end the poll. Thank you.
Thanks. Thanks to everyone who participated in the poll. It's always good to see new participants. Can you go to the next slide? IIESOC as a community has been gradually growing in numbers. We are always looking to add to these numbers. There are different ways in which you can participate in our activities. You can become a member using the membership link on our portal. We do have a dedicated IETF mailing list for the IETF India community. You can subscribe to that. There is also an active WhatsApp group where key announcements are made from time to time. So please do join that as well. You can also find and follow us on various social media platforms that are listed here. Thanks, Dhruv, for posting those links. Can we go to the next slide? This is a call for topics for future RFCs We Love sessions. If you are an author or contributor or say a proponent of a specific draft or a RFC and would like to engage with the community here, please do reach out to us and we will provide you a platform for you to come and present. If you're not an author or a contributor of any draft, but are just interested in knowing or learning about a specific IETF topic, please do let us know what those topics are. And we will find speakers who can cover those topics for you. You can send in your topics via email or ping us on WhatsApp, or reach out to us on any of our social media platforms. We'd be happy to listen to you and entertain your thoughts. And we do intend to bank on this crowdsourcing strategy for our next meetup. Next slide. Before we kick off the talks, a quick note on the Q&A logistics. We would recommend that you use the Zoom Q&A to pose your questions. You can also make use of the raise your hand feature to ask your questions. For any other discussion, please feel free to use the chat and keep it engaging. We will monitoring that. We'll be monitoring that. Next slide. This is the agenda for today. 3 interesting topics and 2 wonderful speakers. We'll start with a talk on computing-aware networking, followed by a talk on SDN southbound interface protocols, and then close with a roundup on IETF 115 and a discussion on what to expect at IETF 116. The first talk, can we go to the next slide? The first talk is titled Computing-Aware Networking Problem and a Possible BGP-Based Solution. Next slide. Before I call on the first speaker, I'd like to say a few words about him. Our next speaker is someone that I personally look up to and have had the privilege of working together on a few topics of mutual interest. He runs a successful consulting company called Old Dog Consulting. He has been associated with IETF for well over 2 decades now and has co-authored more than 85 RFCs. He has been a co-chair of 6 different working groups spread across multiple areas. He has served as a routing area director over a 6-year period. He has also served as an independent submissions RFC editor for a 4-year term. He's currently serving as a technical advisor to my favorite working group, the TEAS working group in the routing area. He has also written, edited, and contributed to 9 books on internet technologies. If you thought he's just a prolific technology author, you're wrong. He has also authored 4 volumes of fairy tales for adults of all ages, and I can personally vouch for how entertaining those books can be. And lastly, he's no stranger to II ESOC community and events. Please welcome our first distinguished speaker for the day, Adrian Farrell. Adrian, all yours.
Thank you, Pavan. I will attempt to share a screen, and who knows what will happen. With a bit of luck, that's working for you all.
We can see the screen.
Brilliant. Okay, so yeah, I'm going to talk about the computing-aware networking problem, and just to say how things happen in the IETF. Sometimes they explode into the IETF with an immediacy that it's obvious, here's something we have to work on. And other things are a really slow burn. And computing-aware networking has been a glowing ember for a couple of years, and some of us have been blowing on the ember, and suddenly it's caught fire. So this is what it's all about. Well, it would be if page down was working. There we go. So I'm going to talk about what compute means and what compute in the network means before I come on to describing the problem and a bit about the use cases, and then talk about the architecture that we'll possibly be using, and then round off this by looking at some RFCs that already exist that may be relevant and how those might get applied in a potential protocol solution. And then we'll just look ahead to IETF 116 and see what's going to be happening. So, compute. I spent a lot of time being confused by what the compute-aware networking effort was all about. So we're not talking about specifically computing, running algorithms on a set of data. And we're more interested in being able to run some program, some function on a server that's remote. So that requires obviously that the program is present, it's been instantiated somewhere, and that the CPU resources are available. But there may be other features as well that are part of this. They could be storage, they could be content, they could be specialist things that happen on specialist processors. So this concept, computing aware networking, embraces everything from actually running algorithms to content distribution to remote storage. And Michael has just posted that the host has disabled attendee chat, which is confusing because he's an attendee and he's chatting. Anyway, I'll get on and leave Pavan and Dhruv to worry about that. So this looks very much like data center processing or edge computing as we've always known it. The processing is done on some computing machine that has the required capacity and capabilities. So why are we talking about in the network? Computer-aware networking. And this is really arisen because of traditional thought about where the network edge is. I think we've sort of grown up familiar with that picture where there are devices attached to the edge of the network, and the network itself is responsible for connecting those devices. But in reality, this isn't about the physical location of those devices. It's much more about the ownership of the resources. So the network provides connectivity from client to server, but the server may be at an edge site, in a data center, or located somewhere just in the middle of the network. And increasingly, network operators are looking to be able to put their server service providing equipment inside the network. And what we care about is how the client uses the network to access the service. So surely we've been doing all of this forever. We've been doing data centers and edge computing and cloud computing, and we're all familiar with it. So what's changed? Why are we talking about something new? I think there are a couple of threads that run through this. One is that services are increasingly hosted in multiple places in the network, not just go to my data center and get it, but go to a data center or a server or a supercomputer or anything, a micro data center. Furthermore, there may be multiple instances of a service on the same server attached to the network. And those servers may have different capabilities. Some may be really CPU rich, some may be quite weak, but still capable of providing some services. And of course, server resources may become overloaded over time. And then the network connectivity to those servers may be different, may have different properties. Some connections may be high bandwidth, some of them may be super low latency. But as demand changes in the network, so those network connections may become overloaded. And then what I think is really driving all this is that new applications are particularly performance sensitive, and they may need rapid responses without queuing or network latency, and they may need sophisticated services to be delivered for them, things that can only be achieved on particularly high capability servers. So what applications are we talking about? Well, really anything you'd like to dream about. Some of the things that have been mentioned fairly recently include real-time image capture and processing. And I know that the police and security services like this a lot, but there are lots of other good applications where it's important to be able to grab a photo and process it quickly. Now, the thing that is grabbing the photo is probably a dumb camera, but it needs an answer back. What have I done? What do I need to do next? Do I need to zoom in? Do I need to follow a particular piece of the image? Multiplayer game servers are pretty big, and I know that in China, multiplayer game servers are big. So what's going on there is people are joining a game with their friends, and they need particularly fast responses, and everybody needs the same sort of latency. Otherwise, it's not fair, because one player can shoot you before you even knew they were there. AR and VR, so augmented reality and virtual reality, have up to now been really things that you run locally, but they're increasingly becoming networked, and a lot of input coming from remote servers. And there, of course, you want good turnaround times. You don't want glitches. You'd like not to walk off the edge of the cliff before you find that there is a cliff there. What else is coming of age? Holographic presence conferencing is something we've seen some pioneering products on, and they, just like Zoom that we're using today, have a centralized server approach, but much higher bandwidth, and some smarts being applied on the server. You've all obviously seen a lot of discussion of intelligent transport, whether this is smart cars or rail networks that are interconnected and event aware, and possibly using real-time image processing as well. So that's needing access to compute that is close to the vehicles, but also has enough capacity to do the right compute in real time. And then lastly in my list is digital twin, with copies of the network being run either on backup copies of hardware or being run on servers to model what's going on in the network. And it might not just be a digital twin of the network, it might be digital twin of critical infrastructure like power plants or factories. So all of these applications and all of the ones that you can dream up all have different network and service requirements. So hang on a minute, what was the problem we were talking about? Well, we can break it down into 5 different pieces. We need to select a remote location to execute a service. So that location must be able to run the service. It must have the resources currently available to run the service. It must not be overloaded. So it's got to be able to meet those service delivery requirements. It obviously has to be reachable over the network, and the network connectivity must be good enough at the time the service is requested to meet the service delivery requirements. So this is not just find the closest first available instance of the service, it's find the best instance of the service. So you could look at this a bit like a traffic engineering problem, where we're not just finding the first shortest path, but we're finding the path that meets the service requirements. But we're also looking at the endpoint, choosing the endpoint according to a group of metrics. So what do we need to know? What are those metrics? Well, we need to know the service locations. Where are the services available? what service capabilities exist at those locations, what are the current loadings of those locations or service instances, what's the topology and the reachability towards those locations, and what's the current state of the metric. On top of all those things that we need to collect from the network and the service locations, we also need to know a bit about the service demand. What are you actually asking for? You're not just asking for, please execute this program, but you're saying, please do this algorithm, do these calculations, and get me an answer in this time, or get me a series of answers with a reliable jitter between the answers, or get me this service and I'm going to send you a huge amount of data. So it's a combination of things in the service demand. So questions that we've seen kicking around the IETF recently have been, can't we just use existing tools, of which DNS and Alto have been high up the list of topics discussed. And DNS is pretty good. DNS is really good for service discovery. It's usually relatively static. I mean, services come and go, but they come and go fairly slowly. And in fact, if a service is flapping, you'd hope that DNS would damp that flapping out so that you got a fairly stable answer when you went to DNS and said, who should I target? And typically DNS doesn't offer the client rather, it doesn't offer much choice. DNS is something where the client says, who should I talk to for this service? And DNS comes back with an answer. So Alto provides a kind of flip of that. Alto gives the hosts and the applications the information that is necessary to choose a location and do its own choice, its own processing, its own choice of who do I want to target for this service request? Where are they based? Okay, now I can set up a connection to that instance and send my request. And that's great, except that's pushing the decision process into the host and application. And neither of these really address the problem at hand, which is we want the client to request a service and the network to choose the best location and network path. So what other approaches might address that? Well, people have talked about load balancing. There's obviously quite a lot of load balancing goes on in the network, especially things like just accessing web servers. So it distributes the load following some algorithm, some policy, but it's not aware of individual service requests or requirements. It just looks at the current loading of servers and chops up the new service requests to go to the least loaded server. Not really taking account of the network, not really taking account of all of the metrics, and so not quite what we want. And there's this thing called message broking, where there's a kind of centralized dispatcher that uses all of the metrics maybe, but it has a problem of being centralized, and particularly a problem if there's really heavy traffic. So what we see is that there's a set of tools out there that address similar problems, but they don't quite hit what we're aiming at here with computing aware networking. So at this point, I need to set out some terminology. I'm sorry about this. It's two fairly dense slides of terminology, but hopefully it kind of leads through step by step in a logical way. So computing aware networking is this business of taking into account the dynamic nature of computing resources and network state, so that we can steer the traffic for a particular service request to a service instance. So that's the big sort of top headline problem statement. And to understand that, we need to know, well, what is a service? Rather legalistic definition: a monolithic function provided by a network operator according to a specification. Well, okay, when I execute a service, I probably better know what the service is. And it's good to know it's being provided by the network operator. Okay, it's not some service being provided externally as an over-the-top thing. This is, I'm going to the network and saying, I want this service, please get it for me. And yes, we can build a composite service by bolting together monolithic services. A service instance is something running in a runtime environment, which could be on a server or a process on a server, that makes the functionality of a service available. So it's like an instance of a program. And it's important to know that a service can have multiple instances running at the same or different network locations. And then we just tag some identifiers to these. A service ID, which is just representing the service. So I've got a nice, neat way of saying to the network, I'd like to execute this service. And this is not aware of the service instance. It's just identifying what I want the network to do for me. And then we have a binding ID, which identifies the service instance that is actually delivering the service in this case. And then to match those two things, we can have a service demand. Please, I'd like to execute this service. And a service request, I'd like to execute this service on a particular service instance. So with all that, we can look at what are the functional components that are actually delivering for us here. And remember, functional components are not things you have to code as separate blocks of function or separate products that you're selling. You can bind them all in together and stir the pot. But from an architectural point of view, what we're trying to do is identify the different things that have to happen in order to deliver computing-aware networking. So we start at the edge of the network, and we say, look, there are these network devices that make forwarding decisions based on CAN information to steer the traffic belonging to the same service demand towards the same chosen service instance. And we categorize those into ingress and egress CAN routers. So the ingress router is the edge router that serves as a service access point for a client, so that when a client comes along and says, I want a service, it goes to its ingress CAN router and says, please get me this service. And the ingress router is steering the packets onto an overlay path towards an egress router that provides access to the most suitable edge site to access a service instance. And this will become clear on the next slide where we have a picture. And the egress router is doing the tail end of that. It's the end of the overlay path. It's receiving the packets and it's pushing them out to the service instance. And then we have 4 lumps that are processing the data that we need to achieve the steering. The service metric agent is responsible for collecting all of the information about the capabilities and status of the service and server at a particular site and reporting them to the path selector. which we'll talk about in a moment. But basically, it's harvesting the current status and capabilities of the servers and reporting that information. And then the network metric agent is doing exactly the same stuff for the network. It's collecting the network capabilities and status, really stuff that we're pretty familiar with about a network, maybe enhanced with things like latency and so on of the network links. And again, that information is reported to the path selector. So great, the path selector is the thing that is determining both the server to use, the service location, and the path towards that service location in order to meet the service demand. So it's looking at what's the service status, what's the network status, what's the demand, and what are the qualities of that demand as well. So what service do I want and how do I want that service? And it's putting all that together and doing a selection of what is the best path and server to use. And then the traffic classifier sits there at the ingress CAN router, and it looks at the packets that are coming in from the clients, filters them, which packets belong to which traffic flow for which service demand, and then steers all of those to the same service instance along the same overlay path as selected by the path selector. Why do all the packets for the same flow have to go the same way to the same service instance? Well, it would be a bit embarrassing if you were trying to do a computation on a big lump of data, and some of the data went to one service instance and some went to a different service instance. Clearly, they've all got to go to the same place for the same service request. So what does this look like in a picture? This makes it all a bit easier. Just to highlight that this sort of architectural picture is my personal opinion, and nobody's really been talking about this in the IETF yet, so it's probable, maybe even likely, that by the time people have talked about this, the shape will change. But what have we got? We've got 4 edge sites, 2 at the bottom. We've got 5 edge sites. I can't count. 2 at the bottom, 3 at the top. The ones at the top have got multiple clients attached or at the edge site. And they're variously homed to CAN routers. So these will be ingress CAN routers. And at the bottom, we've got multiple service instances. There may be instances of the same service or different services, and they're hosted at perhaps servers or in the edge site itself. Maybe it's a data center with thousands of servers and lots of containers, or maybe it's one server at an edge site, or maybe the edge site is a server. Okay, and the edge sites are connected into egress CAN routers, and then everything is connected together with an underlay infrastructure. And what happens is the service metric agent, which can be built into the egress CAN router, or it could be a separate entity. The service metric agent collects information from the servers and the service instances about what's going on and what they're capable of doing. So it harvests that and it sends that somehow to the path selector. So similarly, the network metric agent sitting in the network is collecting information about the state of the network, and it's pushing that information to the path selector. Great. So now a client wakes up and it says, hi, I'd like to access this service. So the CAN router, the ingress CAN router, we'll call on the path selector. And the path selector may be built into the CAN router, or it may be a separate server somewhere. And the CAN router asks the path selector, okay, where should I where should I go with this service request? How should I get there across the underlay in my overlay tunnel? And gets an answer, and maybe the CAN router has to set up a tunnel to do that, or maybe it uses an existing tunnel. And then it instructs the traffic classifier, all of the traffic for this service request, what you've got to do with it is pop it into this tunnel, target the remote egress CAN router, and get it delivered to the right service instance. And then obviously there'll be responses, but the responses are easy to deal with because they're going on reverse path tunnels and they're targeting the client. So it's just it's almost like a layer 3 VPN problem at that point. Okay, that's the picture. So question, should we make this centralized or distributed? And I think this is no different to any other networking problems. The distributed control plane reacts really well to small changes. It's very adaptive. It's strong in the face of network failures, but it's a complex system that requires additional management, and it doesn't coordinate well different client requests on different ingress routers. On the other hand, a centralized approach, much better coordination between service requests, simplifies the network control in the whole network, and so the management's a lot easier. But we're now looking at single point of failure when your centralized system goes down. So, you have to build redundancy, and as you build redundancy, so you're adding a control plane back in. And it's less reactive to changes in the network in particular. So it's always a trade-off. It's no different from all the traffic engineering we've been doing over the years. And the pendulum swings in popularity between fully distributed and fully centralized. And so, a hybrid solution may be the answer. And it allows some flexibility for the operator to choose to push a bit more centralized or a bit more distributed. So question, isn't this just service function chaining? And my answer is yes and no. Okay, we're discovering service instances, just like service function chaining needs to. And we're selecting them, just like building a service function chain. And we're steering traffic to use them, just like building a service function path. So there's a lot of commonality, but it's not the same. So at the moment, we're talking about only one service function being invoked for each service demand. The destination of the traffic in service function chaining is a real endpoint. And here, what we're doing is we're actually targeting a service instance. So traffic does not make multiple service functions on the path to a final destination. But I think that the functional requirements are notably similar. And on that previous list of functional components, you see that they're pretty similar to the functional components in service function chaining. So to talk a little bit about some RFCs that we love, I think it's useful to come back to this and just say, look, a lot of work has been done. There are a lot of tools out there. There are a lot of things that are really popular that kind of build towards this. And I think it's important to get a good handle on DNS and Alto before even starting to look at the requirements that come out of computing aware networking. So go off and look at 1035 and 7285. Those are the foundations, but obviously there are a lot of RFCs that build on that. There are some useful building blocks that we can look at and at least compare with the functional components, but maybe even say, whoa, wait a minute, we've got exactly what we need. So I know close to Drew's heart is PCE. And the PCE, okay, the path computation element that computes paths for traffic engineering and now segment routing, that may be pretty similar to the path selector that we see in this architecture. It's similar because it's selecting paths based on the network information and additional information. And if you go and look at the original path computation architecture in 4655, it says the traffic engineering database may be fed from the network and other places. So the door is already open. And PCE uses objective functions to help guide the path selection. And I think we will find as we progress that we'll need objective functions for how we select paths in computing-aware networking. Do we want to select the server with the most available CPU, or do we want to balance the CPU usage across the network, or what? Okay, so that's building block number one. Building block number two, which will be popular with Pavan because Juniper seems to like BGP a little bit, is BGP link state. BGP link state is this ability of a node in the network to abstract or aggregate or collect and collate network information and then push it northbound to a consumer, either directly to the consumer or through a route reflector to be distributed out to multiple consumers. So the NMA, the network metric agent, needs some way of communicating information out to the path selector. But it's also worth noting that the service metric agent also needs a way of collecting and pushing information out to the path selector. And maybe BGP-LS will do exactly the job we want there as well. So that's a building block that needs to be looked at. And then next I've listed out 5305 and 7810. And this is just an example using ISO-IS. OSPF also exists. But what they're doing is collecting network metrics and extending those network metrics for performance-based stuff so that we can learn what's going on in the network and what the capabilities are. And then I'm going to come on and talk about a potential BGP-based control plane coming out of service function chaining, and that's in 2015. So how does that work? Well, I'm not going to go into great detail, but just remembering that this is not service function chaining, but it looks the same. So maybe BGP can be the thing that solves this. It needs to know about the edge sites. It needs to know about the service function instances and their locations. It needs to select overlay paths. And it's all kind of related to routing. So maybe BGP is not totally a crazy approach. And although we're talking about single endpoint functions and single domains today, I'd be shocked if we didn't end up with multi functions on a chain and multi-domain deployments. Okay, Michael, I'm going to come to your question at the end, if that's okay. So just a recap on 9015. What 9015 does is it uses BGP to announce where the service functions are, and what are the service functions that are located at those service function forwarders. And this is sort of functionally equivalent to the service metric agent announcing the local service functions and their capabilities. It uses the root target to identify the overlay network that's going on. And that's kind of useful because it allows only the edge nodes, like the ingress CAN routers, to listen to the announcements where the root target matches. So there can be a lot going on in BGP, but you only have to pick up the service announcements for the services you care about. It uses the root distinguisher to identify the different service function instances that are being announced, and that's useful again across the many service function instances that there might be in the network. It uses a type to indicate what service function is being talked about, and that matches the CAN service ID. And then it talks about controllers that are used to build the service function chains, just like the path selector. There's a piece that's not needed in 1915 for our use case, and that's actually announcing the service function chains into the network, because we're not dealing with chains, we just have one destination service. But it will make life easy for us when we discover actually, oh, we did need an extra service on the chain. And then also, just per the normal service function chain architecture, there's a classifier which looks at those service function chains that have been built, and is programmed in order to put the traffic onto the right overlay path. So I am seriously expecting that 9015 is a candidate when we start to look at the protocol solutions, but that's a way down the line. So what's the IETF doing about this? It's, as I said, it's been a slow burn. Back in March last year, there was a BOF that was in Vienna and online. And since then, it's been presented in a couple of places, a couple of working groups. I think there were side meetings as well. And that led to a mailing list being set up in October, and another BOF in London in November. And there was a lot of interest in the topic, but it was a very unfocused meeting. And I think they only got about halfway through the agenda before it spiraled into a discussion of existing tools and not talking about the use cases and requirements. But anyway, there was quite a lot of energy. So what we've been doing since then is drafting a charter for what the working group might do. And that's currently out for review by the IETF community. So you've got about a week left. If you care about this topic, go and review that charter, send your comments either to the CAN list or to the IESG, and get them in. We're planning to meet in Yokohama in March. If we're lucky, that'll be a working group. Otherwise, it'll be a BOF. But either way, the intention will be to kickstart the architecture discussions, try to firm up what the functional components are and what the picture looks like, and try to understand what the metrics are. We know what network metrics look like. We really don't know at the moment what compute metrics look like. So we've got to work on that. And there are some internet drafts out there you can look at. They're a little bit straw man early ideas, but they're a starting point for discussion. And my last slide is to look at, well, what could that working group do if it's formed? And the charter says, analyze the problem. Well, yeah. Work on an architecture with the intention to use existing tools if possible. Do lots of groundwork on problem statement and use cases. Might not end up as RFCs, but we've got to understand them. And then my red line here is metrics. As I said, the service-aware metrics are really a big thing for discussion. And then the working group would look into what existing tools can we use and what are the gaps for the control plane, the management plane, and the data plane with encapsulations. So questions, and Michael managed to get in the queue first. When the network decides to change the instance that it is providing a service to my host, will my host learn a new IPv6 address to connect to, or will the network redirect the IPv6? So I think what's going on here is that you are, this is really hard to answer as a protocol question, because it's like, oh, everything's up in the air. But for example, you could target a service using an Anycast address. So you always send your packets to the Anycast address saying, I want to talk to this service. And then the network will handle for you what actual service instance address it will route the traffic to. Does that sort of work, Michael?
Michael, I've given you access to speak if you would like to respond.
Yeah, I don't know how good the quality would be. Yeah, I think so, but I mean, that it's sort of Anycast has never really worked very well with TCP. And if I'm going to have a big bulk upload from this dumb camera, as you sampled, I would hate for the network to change its mind midway, right? On the other hand, I would hate for the network to not change its mind if it turned out the device I was trying to talk to is dead,
right,
or overloaded. So I want both, and so I don't know that I want to have a Anycast address, but maybe I want to have I want the network to give me an address for my service, which is unique to me, but not unique to not doesn't address a specific node, right? The network consistently get good, and so it doesn't have to, doesn't all the cameras don't have to get the same address. They can all have different addresses, and we have lots of V6 to do that with.
Absolutely.
On the other hand, if I have a discovery, maybe it just needs to tell me which connection to use, right? Maybe I need multiple connections.
So I think you've hit the nail very nicely on the head there. You want some kind of sticky affinity between your packets for an individual service request. You want them all going the same way, unless there's some catastrophic failure. And if there's some catastrophic failure and half of your packets have already gone to the dead node, you probably actually need to be told, sorry, failed, rather than have your other half of the packet sent somewhere else, because that just won't do. You need it to be oriented on per service request. So the next time you come in with a service request, it might go somewhere else, and that would be just fine. And yes, you want all of the different clients to be able to send their stuff to different servers, unless for some reason they're all related. And maybe I shouldn't have said Anycast. Anycast as a conceptual idea. How about that? That the client is saying, I want this service from any of these service points, please select one for me. And then one gets selected and you're bound to that for the duration of your service request.
That sounds good to me. The name can't stand. It's too confusing with controller area networks that you find in your car, and outside the ITF there'll be mass confusion, and Google won't help you. So
yeah, I would like to come
think
up
of a
with
better
a different name. Yeah, I'd like a better name because as I said right at the start, I don't think this is compute, and maybe
Agreed.
maybe we could have service aware networking. Oh dear, that's not a good one. SAN got used quite a lot. I did an RFC some years back on the problems of 3-letter acronyms running out. But yeah, any suggestions for a better name, gratefully received. Pritam had a comment in the chat. Do we want to handle that? And then I should probably close and let Dhruv get on with it. So Pritam's comment was that some use cases, e.g. a hybrid classroom, could need shared state and also distributed computing. And how could that be architected? And that's a good question. You need different things computed, but you need some exchange of information between those instances. I don't know. We need to look at that. We need to look at whether those have to be bound together or given a sort of cross-reference so that the service instances know where each other are and how to talk. Or perhaps the service instances have to be instantiated on the same server so that they've both got access to the common storage. We need to work through the use case and find out what we need to bolt on. So I'm going to close at that point. I'm absolutely happy to receive emails offline and talk about it further, or come and join the CAN mailing list. Back to you, Dhruv and Pavan.
Thank you, Adrian. So before we set things up, let me quickly introduce you to the next speaker. You know them very well, but I'll still try and do the honors. They would be covering the next two topics. They are currently working as a chief architect at Huawei Technologies. They have been active at the ITF since 2010 and have been listed as co-author or contributor on 33 RFCs so far. They are currently serving as the co-chair of the PCE working group and also as the co-chair of the Education Mentoring and Outreach Directorate at the ITF. They are currently the secretary of the Industry Network Technology Council. They are a founding member of the IIESOC, where they're currently serving on the advisory board. They have been awarded the Technology Role Model Award by Zinov and have been recognized as a technology stalwart in India. So without any further ado, let me welcome our next speaker, IIESOC's very own, Dhruv Dodi. All yours, Dhruv.
Yeah, thanks, Pavan. Okay, let me quickly move to my presentation. Yes, so let's look at the time. Yes, so I'll try to rush through a little bit. This presentation I've kind of made as a tutorial, and I don't think so we need a whole tutorial here. I'll focus on the key points for this. So basically, now this is mostly looking back at things that has happened. We know that the SDN and this thing has been quite a focus in our industry for a while, and there was a lot of confusions, a lot of things were happening. And this is sort of looking back and thinking of the choices that we have made. What are the various different southbound interface, especially the various protocols that comes under the IETF and routing area, and how they try to answer to the needs of the SDN and the SBI interface, and how do they compare to each other. And right now we have so many SBI protocols. My personal thoughts on where we are going with it? Would we always have all these protocols? Is there a choice that maybe we would ever have consolidation? Let's see. These are just some of my thoughts that I noted some time ago, and I would like to present. So let me move on. I'm seeing the attendee list, and I know all of you guys know SDN well. I don't have to do any recap and none of the tutorial part here. This is what we are talking about. On the top of an SDN controller, we have northbound interface. That's not the scope of this presentation. We are focusing only on the SBI. That is controller reaching out to device and device providing information back to the controller. This bidirectional information in the southbound interface and the various protocol choices that we have in this SBI interface. One thing that I want to add is sort of what are the information. So towards the controller from the network device, the topology is one of the most important one. What are the resource usage? What is the current status? And lately, the key use case also is becoming telemetry. We want real-time data of how our devices are functioning. So that also comes into the SBI interface. Towards the network is mainly configurations. Configuration could be device configuration, services, new services like VPN, services, new configuration, measurements, and also one of the key part about SDN, which was adding programmability into network and making changes super fast. So the programmatic instructions that we send towards the network. One more thing that's kind of interesting is controller to a controller interface that you would not see many folks talk about when we think of an SBI. But multiple controllers is a reality. There's never going to be a single instance of an SDN controller in your network. You would have multiple instances because you need to make sure that there's no common point of failure. Also for scalability, we need to have multiple SDN controller, and there might be a need for an interface between those instances. In some cases, those instances are proprietary. People think of it as like, maybe just a database synchronization mechanism that I could use between these instances so that they have the same data store. That's one way to look at. Another way would be to also utilize the various interfaces that we already have coming from the network. Can they be used and whether they have any role to play, especially because peer-to-peer, that is when you have multiple SDN controller and you would have some interface here. This definitely, we cannot have a proprietary one, especially in cases where we have multiple domains and different controllers from different vendors. This interface may also needs to be from a IETF standard interface. And in fact, IETF had worked a lot on the hierarchy case where you have a parent and a child. In T's working group, we have an ACTN architecture. We call this MDSC and PNC. And this architecture, again, this interfaces that we have, we would like to see if the SBI interface that exists between the controller and this, can they also be used also between the controllers? So that is also a very important thought process that we should employ when we are thinking of what SBIs to use in our network. So what I will be doing is comparing three main SBIs out there, which is BGP, Yang-based, that it could be NetConf, RESTConf, or any of the other management protocols that could be used in this space, and of course, PCEP, which is path computation, a PCEP protocol between PCC and PCE. BGP, I think most of us are well aware of it. It's a exterior gateway protocol. BGP-LS was an enhancement which was sort of very much driven because of the SDN use cases and the need for the controller to learn the network topology. So BGP has a history of answering to the needs of southbound interface. PCEP was in fact sort of like very much built in with an idea of having a central controller and devices reaching out to controller for more information, for specialized instructions. And in fact, SDN evolved, PCEP evolved a lot to answer the needs of an SDN, such as PC initiating information, flow spec, a lot of different things that we did in PC working group to answer to the needs of SDN. and Yang-based protocol, which are mainly for device configuration initially, but again, they were enhanced to do ephemeral changes. They were also enhanced to handle network telemetry, again, to answer some of the needs of the common SDN use cases. But these are not the only one. Actually, you would see if you look at any of the open source controller, and you will see there are so many SBI protocols out there. OpenFlow, of course, is one of the key ones, but even older ones like Forces, SNMP, people still have telemetry information coming from SNMP, so they would like to receive that. BMP is another one, which is a monitoring for BGP. There is a new one like P4. Optical people would use TL1. So all various protocols via which a controller can reach device. But we are focusing today on the three ones. I'm going to skip this whole description about BGP. Basically, this is just a tutorial part, a quick rundown of what BGP is, how BGP-LS works, what is the role of BGP in segment routing. I'm going to focus on the key comparison part and just a mind map of how BGP has been extended, various features that BGP has. One of the key things that BGP does is multi-protocol extension, the concept of an address family, the way to do unicast, multicast, IPv6, VPN extensions, all very clearly by the concept of an address family, clearly enhancing BGP in a particular way. And BGP-LS and flow spec in BGP are another key use cases or key features of BGP that are employed in the SDN space. And now let me move to Yang. Again, a quick introduction. The Yang is a data modeling language. It was done at ITF, looking at what are the issues of SNMP and MIB and how we can solve those issues. That's where NetConf, RESTConf, and Yang kind of got developed within the ITF to answer some of the issues that network operators were facing with the legacy protocols. This is how a typical Yang file looks. A quick introduction to NetConf, which I'm going to sort of skip, and these slides would be available, so feel free to go through them. And most of this information is very basic, which is kind of available for any NetConf. NetConf works on both SSH and TLS. Initially, it was for SSH, later on get enhanced for TLS as well. And this is basically the layering architecture that you could see. Secure transport at the bottom, you have various messages, operations, and then the content, which is the configuration data or the notification data. Similarly, RESTConf is an HTTP-based protocol where NetConf was running on. The RESTConf allow, as the name suggests, more restful in nature. It uses HTTP. Its structured data is in JSON, whereas in NetConf, it could be both XML or JSON. Again, they use the HTTP functions and enhance the whole NetConf feature of create, replace, update, delete, RPCs, all that in the via HTTP methods. So these are the HTTP methods. And let me quickly move on to network telemetry. Now, network telemetry is in fact one of the key things where Yang and network models exceed very well, where other protocols like BGP and PSEP cannot satisfy these requirements. And streaming network telemetry, basically the idea of having real-time data collection, that's where the Yang and the NetConf, RESTConf, gRPC, these functions have been doing really well because they can scale and they can handle the information in the right setup manner. So comparing to SNMP, where you had to do multiple requests at a time to receive the latest information in a periodic way, telemetry just lets you subscribe to some information and then you continuously receive a stream of data as and when data is changed or periodically. And a telemetry system would be able to continuously monitor the data as it's coming in, analyze it, and make network changes, again, using the SDN controller and making changes into the network and reacting to the telemetry information. So this is what is commonly called as a closed loop system in the management space. Okay, so let's move to PSEP. Again, I think I have talked about PCEP in RFCs we love for multiple times. I don't have to go in a lot of details. The history, it's basically started off as a mechanism for a head-end router to reach to a specialized server, ask for a specialized path, because the head-end maybe does not have full visibility or do not have the capability to do complex path computation. So relying on a specialized system was the main use of PCE. It further got also enhanced to handle like inter-domain cases, hierarchy cases, and how do we compute end-to-end path. All those various extensions to PCEP were done over time. Initially, PCEP was stateless. That means it was just a server. It doesn't used to remember things. It had the topology, and that's it. You can ask for path. It will compute a path, and then forget what path he computed and let the state be maintained on the network device only. With the stateful PC, basically a new database came into picture, which is the path database. What are the existing set of paths that are currently set up in the network? That's what a stateful PC does. And having that database allows us to do much more better path computation, because we could see what is the interaction of the current path with the previous path. Various associations could be maintained. And later, this also allow you to do global optimization, not just compute the best path currently, but compute path in such a way that multiple paths are optimized at the same time. And later on, making changes to the path which were already set up in the network based on the changes that are having in the current network. So this is where the stateful PC became more like an SDN controller and was also able to initiate paths and make changes. In fact, we had an extension called PC as a central controller, where it was blending in elements of OpenFlow and SDN into PC, and where the PC could not just reach to the head end, but also to the intermediate nodes in the network and provide instructions on how it needs to behave and set up paths in the network, very much like how an OpenFlow system would do. Segment routing, in fact, and PC and both BGP-LS had a very important part, and segment routing had been a key use case for PC as well, and not just for setting up paths via RSVPT. PC can do multiple cases like PCCC, which doesn't need signaling. Similarly, SR and SRv6 as well. All those things are supported in the PC system as well. And this is sort of, again, a mind map of various interdomain extensions, various constraints, various features that we have. PCEP works not just for MPLS, it supports various optical networks, WSON, GMPLS, FlexGrid, segment routing, multicast, all those features exist. But we don't have, but now we'll go to the interesting thing, and let's compare the three things that we have just talked about. So the most important thing is messaging function. How are the messages formatted in each of these protocols? What is the size of the messages? What is the unit of transaction? How easy it is to implement these messaging functions to achieve the key use cases of SDN. Transport, which is focusing on the reliability and secure of the previous messages. How easy it is to fit the various use cases of SDN. And while we are using these SBIs, how easy it is to deploy, what are the unique features of each of these protocols, and how difficult or easy it is to operate them. What are the network operations feature that these protocols provide? So let's start. Messaging function. If you look at BGP, the model is basically peer-to-peer. You can also use route reflector, and BGP as a central controller is also a model that you will see. In Yang, basically what happens is actually your NMS, which is your client, and your device is called a server, sort of like switch in how we kind of consider like SDN server as the server and the device as a client. In this, the terminology is a little bit different, but it fits the model still quite well. In case of PCC, we have a PCC client asking a PC server. We support a lot of PC to PC communication in both peer manner as well as from parent PC to child PC. Again, fits very well into the SDN architecture. From the messaging point of view, the PCEP BGP basically has two key messages, but also has good support for various address family, which differentiates all these use cases quite well. It uses a concept of NLRI, TLVs, sub-TLVs, everything is encoded in a binary, and root is a basic unit of our messages. One thing to worry about BGP is BGP standardization takes time. IDEA working group requires 2 implementation before anything can actually be standardized. In case of YANG-based netconf and RESTconf, basically we are relying on either an XML or JSON as our messaging format. There is a proposal to do binary. CBOR is one of them, that even these protocol can use binary encoding so that the sizes of the messages can be reduced. The best thing about here is that it's easy to extend, and even vendor deviations are allowed easy in this model, while as doing proprietary things in any of the BGP and PCEP protocols can be a little tricky. The flexibility provided by YANG-based system it's one of the key benefits. PCEP is similar to BGP, but the difference would be we have actually multiple types of messages. We rely on objects and TLVs. We don't have any address family, so that does complicate our messages parsing a little bit as compared to BGP. We are binary, and the key unit for PCEP messages is actually path. Now let's move to the transport functions. BGP is TCP. YANG is basically, when it comes to netconf, it is TCP. When RESTconf, it is HTTPS. PCEP again is TCP, and we have various security features in PCEP. TLS support is there. In BGP, various BGP security things exist, and in netconf and RESTconf as well, the security thing exists quite well. So here they compare quite well with each other. No winner, no losers per se when it comes to transport functions. Use case fit. I think the good fits, BGPLS is one of the best fitting use case that we see of BGP. SR policy stuff, that's also quite well. They have individual address families and this, so SR policies can be easily fit into the BGP messages, and very well suited for IP, MPLS, SR sort of networks. YANG, good fit when it comes to telemetry, inventory, configuration, automation. That's where they excel the best. PCEP excels in traffic engineering networks, optical networks, the PCCC kind of use cases where you are even instructing and programmatic instructions to the devices. That's where PCEP sort of does quite well. When we think of bad things, where use cases where BGP has sort of like not the best fit, is we can't use BGP as a request reply protocol. Again, central controller, telemetry, any kind of configuration. Optical networks, because you will not find BGP there. Again, sort of a bad fit. YANG has an RPC function, so again, path computation request they can handle. The thing would be when you have a huge topology and big data and big fetch. Again, the YANG systems can be a little bit slow. The performance part is where they take a hit compared to binary protocols like BGP and PCEP. Telemetry, configuration, automation is again bad for PCEP. Ease of deploying. Sort of similar, let's compare based on IP networks, optical networks, data centers, and other cases. BGP, already you will find it in most of the IP network on the edge. BGP stack is easily available. Most controllers out there have BGPLS, so I think using BGP as your SBI is pretty good as it comes to an IP network. Again, optical could be an issue. You will not find BGP, but a smaller BGP stack, maybe only having BGPLS is still possibility, but you still don't see it in reality used so much in the optical network side. BGP is present in data center, and it is practical to use BGP in data center interconnect use case. So again, BGP can work well in DC use cases. Other cases is SD-WAN, access network running BGP. That's where, again, BGP can do quite well. YANG-based systems are actually becoming popular everywhere, whether it is IP network, optical network, data center, you would see Yang, Netconf, RESTconf, easy to deploy in all of these cases. PSAP does well again in MPLS segment routing network, also in optical network, because PSAP has a long history of being used in GMPLS optical network. Not so much inside data centers, and not so much for SD-WAN either. Let's look at the unique features of each of these protocols. I think BGP, as I mentioned, address family is one of the cool things about BGP, and it helps in BGP use cases in SDN use cases. Support for multiple protocols. NLRI type is also pretty cool. I think the major drawback would be not straightforward to direct a message to a single device, because that's how BGP is. It's sort of flood. You have to use a lot of policy, a lot of configuration to do that. This is where I think the PSAP would do, or Yang would do much better. And BGP standardization could be a bit slow. Yang unique features would be vendor, private augmentation, deviation, telemetry. Drawback would be verbose, large data handling, and multiple encode formats to support. So implementations can also take some complexity. And I think the Yang model standardization itself, there are multiple versions of Yang models, and within ITF and the industry, we have not been able to converge. So you will see people implementing multiple versions of Yang to achieve the same feature. You will have an ITF version, a vendor version, and even open config version. So that's the part where I think something which is good can also have some side effects. PSAP, the cool things would be how it does interdomain, how it does hierarchy and ACTN use cases, PCCC, how it can be used in IP plus optical convergence use cases. Drawback, advanced features are not yet deployed, and even the interoperability between vendors have shown various issues. So we in PC working group, there is a lot more clarifications coming, even when it comes to interoperability of PSAP standardized features. The operational complexity, BGP is a complex protocol. There's a lot of configuration, a lot of knobs, a lot of things happening here, which makes BGP a little complex to operate. And since BGP is also used to do something very fundamental like routing, we are also always afraid that any impact to BGP could have a catastrophic impact. So that's, again, from operation side, something to worry about. Yang, I feel, would be easiest to operate, easiest to automate. Issue would be multiple Yang models, as I was mentioning. PSAP, I think it's a simple protocol to operate. It can extend to a lot of features. It supports interdomain, etc. quite well. So I am overrun quite a bit. So let me summarize. This is my comparisons slide. And actually, there is a lot more slides which further takes some of the key use cases and compare them a little bit more detail, how it functions with path setup, topology. Oh, sorry, I'm going in the wrong direction. Topology, traffic steering. This is where the flow spec comes in, segment routing, automation, APN, and a lot more things. I will not take up more time, and I have only less time to talk about this. So questions, or should I quickly move to the second one?
I don't see any questions. Maybe, we have about 7 minutes left. Maybe you could focus more on the prep for IETF 116 portion as opposed to doing a recap. I'll leave it to you.
Yeah. I'll try to finish this in as quickly as possible. So moving on, IETF 115 happened in London. This is not a report. This is all just personal opinion. So disclaimer is important. Pawan did cover this in the last meeting, so I can quickly move ahead on this. This is a very important topic. I wanted our community to be aware of it. MPLS headers are being updated. MNA is in very interesting new work that is happening. These are the pointers. Working group last adoption calls are ongoing. Look out in MPLS working group. A lot of things. Again, from T's network slicing, I think we have a framework document. We have a Yang model. This is all nearing completion. So if you care about this, again, a lot of interest has been there from 5G in our community. So I wanted people to have an head up on network slicing work at these. This was also covered, I think, in one of our presentation, the work that is happening in IDR. There are two experimental approaches trying to handle this intent-based routing. There is, in fact, an interoperation procedure also incoming. So focus on IDR if this interests to you. This community and IISOC has been focusing on IPv6 extension header testing in both IPG and V6 ops. We have been working with some students and industry to do some cool measurements and trying to figure out how these extension headers are working. So this was presented both in V6 ops and IPG. This will continue to be a key focus for us in upcoming 116 as well. So if this interests you, reach out. Just CAN is anyway covered. I will talk for a second about TVR. This was a BOF in the last ITF. Now it's already approved as a working group. Cool, interesting things for routing folks here on this call. And there are various different BOFs that happen and new working group in 115 as well. Now, side meetings, I'll quick and move quickly. Oh, some cool photos, which are always fun to look at. Now let's look at upcoming 116, which is in Yokohama. So this meeting is in our time zone. So if you are already not attending in person, so of course that nothing beats attending in person, but do attend online. At least we'll have a good time zone this time. And if getting approval to attend is an issue, the fee waivers for remote attendees are available. Please don't feel shy. Please use this thing to participate. ITF online, that gives you a much better feel. You have remote participation has improved quite a bit. So you will be able to ask questions just like how you have been able to ask questions in this meeting via chat, via raising your hand. So it will be almost as good as in-person participation. So please use this opportunity. Preliminary agenda is actually due today. I don't remember it's out, but look up in the 116 meeting link and you will find it. These are the 4 BOFs that are approved. Though I haven't seen the BOF approval, this thing, but I went to the data tracker and quickly collected this. There is VCon, which is basically standardizing a container for conversation data contained in transcript and multimedia. So again, from application art area. Another one from art area is about email, which is basically automated structured emails, like emails that are automatically sent, and can they be further, not just for human, but for machine readability, and how they can be still using the email format, but having better support for structured email in an interoperable fashion. You would have seen a lot of applications already using this, like calendar applications and other, already using structured data quite well, but now this is coming to standardization. Key transparency, again, how to distribute keys in a safe manner. That's what security area is focusing on. BPF is somebody who is from open source and implementation background, who is well aware of it. There is a new BOF that is happening. They had a side meeting last time. Now they're having a BOF, how to run sandbox programs in a privileged context in Linux kernel. In fact, it's also supported in Microsoft and other ways as well. And that's why they're coming to ITF and finding out what can be standardized now in this space. So quite a few interesting BOFs as well. And BOFs are fun to attend because this is where the working just starting. You don't need too much background knowledge. You can just win with the whole ITF community. Whereas if you attend a working group like MPLS and there's a lot of history of over so many years that sometimes may feel daunting. Now, key part for those who are new, how to participate, like do some groundwork, identify what interests you. If ITF work is new to you, pick at least 1 or 2 key working groups that you care about, go in depth into them, monitor a few more. Mailing list is the way ITF functions. So you need to join the mailing list. Some people I know get daunted with too many emails and they don't want to clutter. Maybe use a different email, like how I used dhruv.itf@gmail.com. Use IMAP if that's what interests you, where it will not clutter your mailing list. Whenever you have a free time, use your IMAP to go and browse the ITF mailing list. But start doing that and prepare for the meeting. Go through what is being discussed in the working group before you show up at the meeting. Participate in a lot of fun things that happen, like IPG, hackathon, technology deep dive, side events. So these things can equally be fun apart from the main working group. So look out for the side things that are happening along with ITF. New work is easier to participate in. Dispatch working groups are fun because that's where they're discussing initial work. So if you're new, these would be my tips for you to participate. These are all the links for the mailing list, for the meeting, for the fee waivers, and all the things that you need to know about 116 as well. And oh wow, I come 1 minute left.
There's a question on the chat. It's a
Yes.
question about getting announcement of BOFs. Do you want to take that?
Yes. So BOFs are, if there is an ITF announced mailing list. So if you don't want to, if you want to know what are the announcements, they will not be flooded with a lot more data. This is not like the other mailing list where there would be a lot of discussions. So at least please register to ITF announce. And on ITF announce, you will find all the agendas, BOFs, and all the things coming in. If you go to the agenda page, you could search for the key term BOF as well, where they will be clearly mentioned. ITF blog would also be a place where the blog proponents will come, and like even the ITF chair would give an introduction about various blogs that are approved by the ISG. So in all these places, you will try to find information. And within our community, I will try to pass all that information in our WhatsApp and our mailing list as well, if that is found to be helpful.
Okay. Thanks, Dhruv. I think that brings us to the close of this session. Thanks to Adrian and Dhruv for their presentations. The material that was presented today would be available on the portal. So if you have any questions, feel free to follow up with the presenters. Thanks to all the attendees for participating in the discussion. It's Friday evening, and we appreciate your time here. We do look forward to your feedback on the topics for our next session. Stay safe. Enjoy your weekend. Thank you.
Thanks, everyone. Thanks, Adrian. Bye. Have a good weekend.